All right, let's continue. So we're in 1.4 of the section here, and we're going to quickly go over solving all the different types of equations here. And again, this is going to be probably a little more involved than we've seen in algebra. The problem's a little bit tough, but not too much tougher. And again, all the different variations here. So sort of, you'll probably see more like the ones that you've sort of done towards the end of algebra. So with that here, so again, some ones that you should probably already know what to do. So all yours, try it. A lot of more quadratic problems to solve. And remember 1.2, we did all the stuff about factoring. Remember that good stuff? That was 1.2. 1.3, we went into the complex number system. So we learned about the I value. So now sort of throwing it all together into solving any and every type of algebra problem. This is 1.4. Cool, all right. The way I would do this here, first of all, I notice that there are 4 terms here. And if it's 4 terms, then I notice I can't factor anything out of all of it here. There's nothing that's common to all of them. So right away, I think to myself, factoring by grouping. Is that right? And again, for these ones, if I think you probably should know it, I'm going to just let you try it yourself first. Then we'll do it together. If it's something pretty much new, then we'll go through it together. All right, and we know this too. What we do for factoring by grouping is take the first 2 terms, put into the first parenthesis, the last 2 in the other one, and then careful here. These are the tough ones because you have this little minus here. So the negative goes with the x when you do that here. So tell me if you guys agree. X squared gets to be factored out of the first parenthesis. Yes. What gets to be factored out of the second parenthesis? Yep, cool. And then we usually put a little -1 just so we have a value there as opposed to just a negative. And left over is x plus 2, exactly how we wanted it. Factoring out the common term to both of those. In algebra, this is called factoring out a binomial expression. Left over is x squared minus 1, and the question is, have I factored it down completely? Wow, that's cool. Okay, that's interesting. And no, because there's some more stuff to factor. Are we good there? So a little bit more factor intense in 1.4. Okay, but once you get down to this level, I think you guys should go directly to the answers, right? You don't need to split them off 3 different pieces. Just go directly to answer. And so the answers are -2, -1, and 1. We good there? All right, they don't have to be in this order, but all 3 answers need to be there because all 3 are the answers to this solution. All right, and again, let you guys try. And again, tell me to go back if I'm going too fast. Otherwise, we'll just keep on speeding along. I'll sort of look up to see how you guys are doing over there, and if I think most people have written it, we go from there. It's all yours for this one. And all right, when factoring, we did cover this in 1.2. When factoring, we do want to move everything over to set equal to 0. And then from there, I think you guys should know exactly what to do here. hopefully you guys are done. Factoring out the x squared leaves us with x squared minus 4. If that is the case, we can factor down some more. How about x plus 2x minus 2, and then each of them set equal to 0 eventually gives us answers of x squared is equal to 0. So how did I do that step? What did I actually do to solve for 0 there? Bless you. We talked about it last time, right? Really what I did is I just took a square root of both sides, right? When we do plus or minus a 0, we still get a 0. We're good. All right, how about 0, -2, and a positive 2 at the end? Okay, this is the way it's usually written in the back of the book. So I'll sort of write it like that. This is called set notation. It just means each and every one of those elements in the set is a solution. That's good. All right, let's keep on going a little bit more intense. How about this one? All right, those of you that are looking up at the board, remember, again, when you think about factoring, you always think about moving everything over to set equal to 0, because that's where it starts here. So moving over the 4x will give you a minus 4x. Moving over the -20 gives you a positive 20 or plus 20. And then that goes into factoring by grouping. Hopefully you realize that as well. So again, setting this up like we did for practice problem number 1. So can you finish that off? I'm going to put down some of the answers here as we go. Just kind of look up if you think you've got it here. Factoring out an x squared out of the first set leaves us x minus 5. Factoring out a -4 out of the second set gives us another x minus 5. And again, using the grouping method, factoring out these binomial leaves us x squared minus 4. And of course, yes, that factors down some more as well. X plus 2x minus 2. And then eventually, how about I got 5, -2, and positive 2 in my final solution set. Okay, so really those 3 problems just to give you an idea that you got to keep on factoring till you get it done. And then throwing in some extra stuff from 1.3, it may be on the homework you might get complex answers after this, so kind of be mindful of those as well. Okay, but let's go on here. So that's done. How about let's go to rational equations. Remember these guys, where they are in fractions. Particularly what we have is we have variables that are in the denominator. Okay, there's 2 different ways to do this here. The problem that we have here is the domain issue. Remember last time we talked about domain? When do we have domain problems? When we have a fraction, right? And the other domain problem is when we have square roots. In this case, it's the first one. So we may do off to the side if we wanted to. We can actually make a little domain problem area here. But in order to do that, we still have to factor the bottom. So let's do one step here. Let's factor out any denominators if we can, because that will lead us to domain a little bit easier. So 1 over x, nope, that does not factor, but yes, 5x plus 10 does factor. So how about factoring out the 5 leaves us with x plus 2. Everybody good there? All right, here, so off to the side, what we have to do before we do this, and we're going to have to ask ourselves, what can x, because of domain restrictions, what can x not be? Yeah, can't be a 0, because they'll cause the problem right here. And then it also can't be -2. There they are. If I get a 0 or -2, then there's no point in doing that, because if I were to plug in a 0 into this equation, or if I were to plug in -2, there would be come on, indeterminate forms, right? Or you guys help me out. What's the word here? There you go, undefined, right? Undefined numbers, which doesn't make sense in mathematics. Okay, but let's go for it. How do we do this? We got to find something called the LCD, is that right? What is the common denominator? In fact, what we want to do is the least common denominator, which is the smallest one, because we can get bigger and bigger numbers. But what we do is we look for, maybe the first one is to look at the coefficients. I got a 5 over here, I got a 5 over here. I'm going to have to need a 5. That's given. Then look back over here, look at all my monomials, this little x right here, I'm going to have to need that x over here too. Then look at any binomials, x plus 2, I'm going to have to need that too. So there's my least common denominator. We good? And this is the smallest denominator possible. So kind of careful, because students, if they're not trained in algebra, they go a different direction here. Don't do it. If you have an equal sign and you actually are solving an equation, if you're doing that, we're going to use this to multiply with. We good? If you're not solving an equation, you're just simplifying an expression, then we would make common denominators. We don't want to make common denominators. So what we're going to do is we're going to multiply 5x times x plus 2 times 1 over x minus 12. So basically we're going to multiply the whole entire left side and the whole entire right side by that common denominator. All right, and since you guys are sophisticated Math 15 students, I think you guys can do that easily. So distribute this 5x times x plus 2 into here. Think about what's going to cancel. And then 5x plus x plus 2 into here, and think about what's going to cancel. Alright, so let's go for it. As we plug this into here, what's going to cancel? X is gone. So that means I'm left with a 5. I'm left with x plus 2 times 1. So it's really going to be 5 times x plus 2. Minus sign. As it multiplies into here, let's see, 12. Well, the 5 is going to cancel. The x plus 2 is going to cancel. So I'm just left with an x. Let me erase that actually. I don't want that in there. Okay, all the way at the end over here, there's a 5 here, 5 here. Those are going to cancel, so we're left with x times x plus 2. Hey, we're right back into factoring again, aren't we? Problems 1, 2, and 3 again. So I'll let you guys have a minute here. Try to go as far as you can on this one here. Multiply or distribute wherever you need to. From there, since you have an x squared, you're going to set equal to 0 and eventually try to factor things down. Alright, let me start it here. Those that are staring up at the board here. Let me rewrite what I had before. That's what I had before. And let's multiply the 5 in. So 5x, 5 times 2, x times x, x times 2. Alright, simplifying each of the sides, I guess we should do that first. So the only simplification is the 5x subtract 12x. That's the only thing I see. So 10 minus 7x is equal to x squared plus 2x. Is that good enough there? And again, if you want to stay ahead of the class or you sort of feel like you're falling behind, I suggest reading ahead. I suggest maybe trying the practice problems before you come to lecture, because that's exactly what I'm going to do, and then for you just sort of putting pieces together. Okay, this way it kind of depends which way you want to go. You can either subtract the 10, add 7x to bring everything over to the right hand side, or you can move everything over to the left. It doesn't matter which way you go. What I did is I moved everything over to the other side. Good there. And the reason why I moved it over to the left side, to show you a little something. That's about it. So what I really did is I subtracted x squared, subtracted 2x, and then subtract 2x with a minus 7x gives you a negative 9x. Okay, here's the thing I want to show you. This little negative x squared, we don't like to factor stuff that has a negative in front of it, in front of the x squared. So all we do to get rid of that is we just multiply both sides by negative 1. And once you do that, that looks more like a factorable form right there. So I need two numbers, multiply negative 10, add to a positive 9. Got it with that. 10 and negative 1 would work. Positive 10, negative 1. If that is the case, then the solutions are there. We good? And then the only thing you got to check, you got to go back and think to yourself, does it fit my domain restriction? Yeah, it couldn't be a 2. Sorry, no, it couldn't be a negative 2. It couldn't be a 0. But negative 10 and 1 are just fine. Okay, so most math textbooks, that's the way they would do it. They put a domain restriction first, then they would solve a rational equation. Some math textbooks, like yours, what they do, they just start solving the problem. After they solve the problem, they go ahead and plug those numbers back in to check if it's going to cause an undefined term. We good? Doesn't matter which way you go about doing it. I think this is the more thought through method as opposed to just sort of do the problem. Then you sort of see what you're seeing. Cool. But again, you can always check by plugging stuff back in. Cool. All right, so I give you this one here from start to finish, all yours. Can you guys do this one? So think about your domain restriction. All right, and if you're done, maybe check with the neighbor next to you to make sure you guys have the same exact answer, if you do have a neighbor. All right, I'm going to start it as well already here, just sort of So we're not having to go completely over it here. So factored form, just kind of look up if you really are stuck, but if you're working on it, keep on going. Alright, so the only factoring that needs to take place is x squared minus 4. Alright, and looking at this now. I'm going to write my little domain restriction here. So x cannot equal. Are we okay with 2 and negative 2? All right, and I think the least common denominator is pretty easy to get, right? X plus 2x minus 2. And that's going to multiply the whole entire left side as well as the whole entire right side. And again, as things factor in, here x minus 2 cancels, so I got x times x plus 2. This one's a minus sign now. X plus 2's cancel. How about 2 times x minus 2? Here, everything cancels. That's great, because I just have a 4x. I'm going to rewrite that bottom as well here, just real quick here. See if you guys still working on it here. I'll let you guys maybe half a minute here try to finish it off here. Let me rewrite that piece there, the last piece on the bottom there. Okay, so distributing the x, distributing the negative 2, kind of careful here, that should be a negative 2x plus 4. And gathering together like terms, hey, that's no fun. 2x minus 2x cancel, so I'm just left with this, x squared plus 4 on that side. Again, moving things over to the left-hand side, setting equal to 0. At this point, you have kind of funny, it's x minus 2 and another x minus 2 as your factored forms. Alright, whenever you see that here, I think we saw that in the previous chapter here. Whenever you see two things that are exactly the same, you don't need to solve for both of them because you're going to get the same answer anyways. Just take one of them and solve it in your mind. X equals 2 and we're good, right? See if you people shaking their heads, no, Mr. H, we're not good. What do you mean? Going back to our domain restriction, we said that it can't be 2, it can't be negative 2, because if I plug it in, it makes undefined terms. So even if you check it, and again, that's the whole point of checking it as well. Once you plug this in, that first fraction is already a problem, right? This will give you 2 over 0, and you can't have that as a number. That's not a number in mathematics. So therefore, the answer here is no solution. If it came into x minus 2, maybe like x plus 3, then we couldn't use the 2, but we could use the negative 3 as an answer, right? Okay, there are some equations where it's probably easier just to check the answer and be done, as opposed to trying to figure out the domain. So for the rational equations, it's a lot easier to figure out the domain and work from there. The next set are these. And before we get to that problem here, let's have a little conversation why that is so. So let me do this. Bless you. All right, why are the square roots a problem, especially when we're solving equations here? Well, they do have a domain restriction. But even more so, we have this little problem here. Tell me if you guys agree with this. Is that true? So if I were to square this side, and if I were to square this side, everything's still good, right? That's 25 here, that's 25 here, and I can keep my equal sign, is that right? Okay. But how about this? True or false? Yeah, that's false, right? Negative 5 is not equal to 5. But here's my problem. If I were to do this, now do I have myself equal sign? Okay, so here's the problem with square roots. Whenever you are the one that's going to be squaring both sides of an equation, it could be that when you get to a true statement, the previous statement was also true, but it could be if after squaring you get yourself a solution, it could be that the original problem itself, before you squared it, was actually a false statement in the beginning. We're good? That only works for square roots, fourth roots, sixth roots, because those are all even numbers and the negatives fall away, right? It's not true for this. Good then, this would be 125 on one side, 125 on the other. Everybody agreed there? Jumping over here. Everybody good there? And if I take it to the third power, I still, hey, my negative is still there, is that right? In that case, I can still keep this little not equal to. The problem really is square roots, fourth roots, sixth roots, any kind of even root. So if you are going to square both sides of an equation, you're going to take both sides of an equation to the fourth power, you have to go back and check your answer to make sure it was this case and not this case. We're good? So in these guys you have to check. No other way around it. So let's start with that. So look at this problem here. Let's see, I have a square root. The only way I can get rid of a square root is if I just square both sides. And the little math term is that we say there could be something called extraneous roots. Whenever you square both sides of an equation, take them to the fourth, sixth, or eighth, or any kind of even power, possibility of introducing extraneous roots into the answer. All right, but let's go with it. X squared is over here. The square root and the square cancel each other out completely, and we are wonderfully left with that right there. And then your choice, whichever way you want to go on it. I think I'm going to move everything over to the left. That's just me. I like moving everything over. And then you probably want to put them all in standard form. Remember, standard form is the highest degree to lowest degree. All right, again, got the little negative out in front as our leading coefficient. I don't like that. So in my mind, all I'm going to do is multiply through with a -1, or I can just switch all the signs. Cool, all yours to finish up. Okay, let's go for it. So hopefully you factored out the x, leaving you with x squared minus x minus 6. In that case, that does factor down into x minus 3 maybe, plus 2. And then at that point, then you got yourself the answers. So I got 0, 3, and a negative 2. Are we good there with those? And if you stop there, you're wrong. Because what do we have to do now? We got to check each and every single one of them to make sure it makes sense. So got to check. Check x equals 0. Plug it into the original problem, and the question is this a true or false statement? Yeah, that's true, right? 0 subtract 0, square root of 0 is still 0, so 0 works. That's cool. All right, how about the 3? Plugging in the 3 value into it. Ooh, that's going to be a tough one here. Got to do work here, so that's going to be 27. Yeah, 27 subtract 18, and that would actually be a 9. Hey, that does work. That's cool. Okay, 3 works.
Was it negative 3 or positive 3?
Ooh, positive 3, and a negative 2. Yeah, I can go back real quick here just to make sure. Let me do it. Let me go back, and then we'll go forward here. The question is was it positive 3 or a negative 3? The factored form was x minus 3, so the answer is x equals 3. Cool. Yeah, I'd rather check and then not check here. So let me go forward to where we're at. And cool. Okay. X is equal to negative 2. Let's see if that works. Negative 2 times negative 2 times negative 2 is negative 8. And then we got ourselves a plus 12, so we got a square root of 4, and I don't think so, right? Square root of 4 is a 2, not a negative 2. That is not correct. So really the answers are 0 and 3. The previous math book that we used to use for algebra, I remember we always used to say these are potential answers, and it made you always check it by checking it and then making sure that it was the correct answers. So always had to plug stuff in at the end. Okay, are we good with those? What you should notice though is the issue is not so much that if it works out, or I guess I should say there's a little trick to it here. You guys remember the square root? The square root here, or the principal square root, it can only give you a positive answer, right? So let's go back to the original problem itself. I just want to see here. I'm going to go backwards here just to sort of show you something. Notice the x by itself is equal to a square root of all this right here, right? So notice you have this situation happening. Can x ever be negative? No. If you have x all by itself equal to this little square root, there's never a time that x could be a negative number, right? Because it's impossible if you're taking the positive value of this. So that's kind of sort of you sort of see as the issue. Okay, so let's go. Those are easy to see if you can need a negative or positive here. There's practice problem number 7. This one's not so easy to see. So yeah, you do have to just sort of work out the problem, be done, and then just check them. That's all. All right, a little hint I'm just going to tell you is you want to move everything over so that the square root is all by itself first before you square anything. Alright, so here's what I would do. I would probably move the 2 over to the other side. There it is. My square root is all by itself now on one side. Because if it isn't, then you're not going to get to be able to cancel off this little square root term, or this little radical. Once that isn't in place, let's square both sides. So 6x plus 4 is equal to, and then we got to do some some work right over here. Alright, and if you don't know the little special form, how to multiply out a perfect square trinomial, then you got to do it off to the side. Put an x minus 2 times another x minus 2. See what happens here, but you should get an x squared minus 4x plus 4. And if you know the little special rule from factoring, then that should be easy. Square the first term, take the 2 and the x multiply together times a negative 2, because that guy, and then you square the last term. So, pretty easy. Okay, we got ourselves an x squared again. So here it is. Let's move everything over. And this time, I'm going to move the 6x and the 4 over. Factoring that out. And again, set each of them equal to 0, or just give me the answer, whichever you like. I'll go with, let's see, x equals 0 and x is equal to 10. Is that good? All right, and the question is, are we done? No, we have to go back and check. So let you guys check just to make sure which one works, or both works, or none of them work. Question? No, we're good? Okay. Alright, let's check the x equals 0 then. Plugging it in again to the original problem itself. You can technically plug it into up to the point that right before you squared it. So it could be the first one or it could be the second step we did. But before you did the squaring step. So 0 does not work. It does not produce what I needed to produce. Okay, so then let's check x equals 10. Plugging in 10 in for the x variable. Let's see if this works now. That's going to be 60. 60 plus 4 is 64. And again, square root of 64 is 8, and then 8 plus 2 is going to be 10. That's going to be a good one. So that does check out. So the only answer here is really 10. Okay, how can I complicate things anymore? Well, so far we've been dealing with a single square root symbol. The complication comes in is what happens if you're dealing with two separate symbols at the same time. That's the fun part. And again, notice we're doing a lot of algebra. I think I said this before, calculus is really algebra on steroids. If you have a very, very good solid grasp of algebra, you're good. Calculus will be easy for you. I remember at Fresno State, I was having issues with my first semester calculus class there, and walked into the professor's office hours. I said, you know, I'm having trouble with this step and this step and this step and this one and this one and this one. So he looked at the problem and he was going through it. He says, your problem is not calculus. You're grasping the calculus just fine. Your problem is the algebra. So then he threw at me a algebra book and he said, go study chapters 4, 6, and 8. and don't come back until you do so. And so it was, wow, I got this now. But it had to be that. It's really algebra skills. Okay, so practice problem number 8. What do we do when we have two radicals at the same time? We have to isolate one of the radicals. Just one, it doesn't matter which one. I can either move this guy over, leave the x squared by square root of x by itself. I can move this one over, leaving us with the x minus 5 by itself. Your choice, it doesn't matter. What I'm going to do, I'm going to move the square root of x over to the other side. So subtract square root of x, move it over here. That means we have the minus root x by itself here. Once I've done this, what I get to do now, since I've isolated a radical all by itself, and in the previous problems they were already isolated, but let's square it now. It looks kind of funny at first here, especially on the right hand side, but I get x minus 5 on the left because they just canceled each other out and that was it. Off this one, you may want to have to do this off to the side here. So 5 minus radical x times another 5 minus radical x. Let's see, FOIL method gives me a 25. 5 times a negative root x, so it gives me a negative 5 root x. Outside term, inside term of FOIL, hey, it gives me the same thing again, huh? Negative x, negative square root of x times 5 is negative 5x. Negative square root of x, sorry. This is the toughie. So negative times a negative is a positive. What's a square root of x times another square root of x going to give you? Just going to give you an x, huh? Because you just formed kind of like the square root of 7 times another square root of 7. Give you square root of 49, but then it will just be back up to 7. So plus x. Adding this up together, so let's see, I got a 25. If I add this second column, I get a negative 10 square root of x, and give us another x at the end. So notice what we've done. By isolating this radical by itself and squaring it, we got rid of this guy, but we haven't got rid of this guy yet. But at least we're getting closer. Now we only have one radical left. So now the question is, can I isolate this radical now? Absolutely. I'll let you guys do it. All right, let's see what I'm going to do. I'm going to subtract x from both sides, and what happens there, the x go away. I'm going to subtract 25 from both sides, and if I do that, I give myself a negative 30 over here. On the other side, a negative 10 square root of x. And then I'm going to divide through by negative 10, so therefore, voila, I've isolated that radical by itself. Once I do that, then the game begins again. It's easier though, usually. Square both sides. I'm sorry, square both sides, you get x equals 9. Are we sure that's the answer? Nah, we're not sure that's the answer yet. All we can do is plug it back into the original problem and see if it actually is the solution set for it. Plugging in the 9 right there, and again asking us the question. This is the square root of 4 plus the square root of 9. That's going to be a 2 there, that's going to be a 3 there, and when you add them together, sure gives you a 5. That's cool, that works. Again, the way it's going to be listed in the back of the book, just be 9 in set notation. Okay, so up until this point, I think you've seen these before in algebra. I'm sure if you went far in the Math 63 textbook here. This one, it's going to get a little more complicated. This one you may have not seen, so let's go into this one here. What happens if you have fractions in the exponent? It's still radical technically in form, but we got to think about a few things here. So this little piece right here is what we got to think about. And we're very much interested in what's happening in the numerator of our exponent. That little one right there. If the numerator is odd, what we do to get rid of stuff, we take the reciprocal of the fraction, the exponent, and we put that reciprocal on this side. And then we're pretty much done. We're solved for u. If m is even, we got ourselves a little problem. Because, again, that little situation, it could have been originally been a negative or it could have been a positive. We don't know. And that's our problem. Let me at least give you maybe a quick illustration here, I guess. And this one's somewhat abstract, so you really have to think through as you do these here. But the giveaway is when you're dealing with solving an equation, you isolated that base with its exponent. You got a fraction of the exponent, and the numerator of the fraction, the exponent, is even. At that point, you got to think about a few issues here. So before we get to the problem itself, let's kind of explain what in the world that is all about. Let me go to a little separate page here real quick. Now let's at least try to explain a little bit here. Okay. So first of all, let's think about this here. Do you guys remember that this guy here, n square root a to the m? Remember that guy? We can change this from radical form into exponential form into a m over n. Are we good there? Okay, so let's put in some numbers here to see if this makes sense. I got a third root of 2 to the 5th power. Good there? If I do that, it's going to give me what? 2 times 2 times 2 times 2 times 2. Give me a cube root of a 32. Everybody good there? And notice I'm not going to really solve the problem here. If we can, let's see. What do you guys say here? What's the solution here? Oh boy, we're in trouble here. Is this 8 times 4? Cube root of 8 times the cube root of 4, and eventually I get myself a 2 cube root of 4. Everybody good there? What we really are interested in is the signs, that's all. Notice we went from a positive number, we went this way. Okay, let's go a little bit a different one here. Cube root of 2 to the 4th power now. Again, and these problems are really from my head. Spontaneously trying to explain this subject here. So 2 times 2 times 2 times 2, anybody? 16 it is. 16 is actually 8 times 2. And we can split off these cube roots into an 8 cube root of 2, and we get ourselves a 2 cube root of 2. Everybody good there? We're getting somewhere. We're getting somewhere there. Okay, the problem comes in as this right here. So this is cube root of a negative 2 to the 4th. Cool. If I do this here, notice what happens because I'm taking even powers of something. The negative goes away on me. That's my same problem when I'm solving equations here. I want to be able to go back and get back to a negative 2, and I can't. So good. So this guy, just to finish it off here, this would be a 2, 8 times 2, which then gives you a 2 root 2. Everybody good there? But here's my problem right here. I start off with a negative 2. I end up with a positive. My negative just sort of went away. So let's go back here. So what that really translates, let me give you this situation. What this really translates, it's the cube root of a to the 4th And what happens is I get a to the 4 over 3. So notice in my numerator, I have a even number. Because that even number is there, when I start taking even powers of stuff, the negatives go away, and I can't let that happen, especially when I'm solving equations. Cool. Okay, so let's try 2 problems here dealing with that issue. First one, and again, recognize real quick here, in the numerator of the fraction and the exponent, even or odd, as you guys writing it down. This is like heavy duty algebra here. She whiz, we're jamming. So what you really need for calculus, in a sense, is a good grasp of algebra, a good solid grasp of geometry. If you got those 2 things in common, you're doing good. That's what we're going to do a lot of. Again, chapter 1, humongous amount of algebra. The rest of the time we're going to do a lot really more of graphing. And we'll take a look at the graphing aspect of linear equations, the graphing aspect of polynomials, quadratics, exponential, logarithmic, all that good stuff. Okay, let's go for it here. So, trying to solve for x. Guess what I would do first is subtract that 4. Next, I probably divide by 3. Notice the 3 all the way in front there. I want to get that little binomial all by itself. So, divide both sides by 3. I got myself a 1 now on that side. Alright, and according to that slide that we had the formula on, I have myself a 3/5. How do I get rid of that 3/5? And if you follow the formula off that's not going to quite give you the mathematics behind it. But remember doing this here? All we're going to do is take the power of the reciprocal of it. Whatever do to one side, better do to the other. So that's 5 over 3. Sorry for case. Okay, that's a 5 divided by 3. Because what I want is I want the 5's to cancel, and I want the 3's to cancel. That's what I'm interested in. So it's taking power of the reciprocal of the exponent. X minus 2 is left behind. This one you should be able to do. So the 3rd root of 1 is 1, and the 5th power, still 1. And got myself a 3. So what that little formula slide was talking about, as long as this 3 here was an odd number, I don't need to check anything. I can go do this. Once I get to here, that is the answer. I don't need to check anything. I got everything. It's all good to go. Of course, there's always a 9b. Alright, I think you guys at least know how to start it here. I think we're going to isolate that 2x plus 1. So what should we do? I thought I heard it. Add 7 to both sides, is that right? At least get that 7 to the other side. Alright, so here's where we think about it here. Notice I have this little even number on top now. So that was the little problem, because this could have been maybe like a negative number, but if I raise it to the 4th power, I lose that negative aspect of that number. Could have been this was a positive number. Taking the even power, it would have still given me the positive number. Good. We're sort of losing a problem, losing an answer there. That's the problem. Okay, so let's take the reciprocal, both sides. Or the reciprocal power, I guess I should say. The 4's cancel, the 3's cancel, except the only thing is, since 4 was a even number, what we have to do is we have to say that original number could have been, there's my little negative positive. Okay, got some people looking at me like I just came from the moon here. So let's go back. This is what I'm looking at right here. I'm looking at u, in this case it's 2x plus 1, to the m over n. So that's 4 over 3, is that right? And m is even. So what I did is I used the reciprocal power on the other side. And when I use the reciprocal power, I got to keep the concept of that k being a plus or minus. Two possibilities for that k. Ooh, let's see if yeah, didn't do that. Okay, let's see where we're at. Yep. Anyway, right. Cool. Okay, let's take negative 2 and a positive 2 to the third power. So that's going to give me a plus or minus 8. Is that right? At this point, you could probably split them off two different pieces here. I got to solve the one that's 2x plus 1 is equal to positive 8, and I got to solve the 2x plus 1 is equal to negative 8. So in this case, you don't really have to check it, but you do have to understand when do you include that little positive negative, or when do you don't. Alright, solving it. Hopefully you guys did it here. So subtract 1 gives you 7, divide by 2 gives you 7 halves. This one, you're going to subtract 1 gives you negative 9, divide by 2 negative 9 halves. And again, no need to check as long as you understand that little plus minus situation and get yourself both answers. Cool. Alright. Alright, one other set of stuff I think you've seen in Math 63. We call these quadratic in form. This little part right here. We call quadratic in form, which means it's in the form, just the exponents could be a little bit off. So AU to the second plus BU plus C is equal to 0. Isn't that what we usually want? We want something squared, followed by that something to the 1 power, then followed by a constant term, right? That's the trinomial that we usually factor. So let's go for it here. I'm going to try to solve this guy. Alright, looking at this one here, so notice you have something taken squared and then taken a cube root. Then you have this something taken the first power, cube root, and then you got nothing. So here's a little trick. Well, here's a substitution we need to make. I need to make it so that it's not 2/3 and then 1/3 and 0. I need to make it so the degree is 2, then it's degree 1, and degree 0. So it goes down in that order. So we do something called the U substitution. And what we usually do is we take this little middle term right here. Why do we use the middle term? Because if it goes down to degree 2, down to degree 1, that little middle term of degree 1, that's what I want. So U is going to be x to the 1/3. You might have to play with it just a little bit here to get it the way you want it. But let's see if this makes sense. Isn't x to the 2/3 really x to the 1/3 squared? Isn't that really the same thing here? Remember how we multiply exponents? So if that's the case, and if u is actually x to the 1/3, doesn't that make sense that now this is technically just u squared? Minus 7, and then u is that x to the 1/3 plus 6 equals 0. Can we factor that down? Hey, yeah. Now it's degree 2, then it goes degree 1, then your constant term. Okay, why are you guys being introduced to u substitution? Because second semester calculus, that's all you do, is you do u substitutions for something called the antiderivative. You learn all the different 81 plus formulas. So there's 81 different possible u substitutions that you guys learn. Whew, good stuff. Can't wait. Okay, so let's see. U times u gives you u squared. I need two numbers. Multiply 6, add to -7. -6 and a -1 would do it. And if that's the case, I can set each of those equal to 0 and solve. So how about u is equal to 6 or u is equal to 1? Everybody good there? The only little problem we have is we didn't start off solving for u. We start off solving for x. And so what we do is we back substitute the x in. So u is actually x to the 1/3. Now equal to 6. On this side, it's u to the 1/3 is equal to 1. All right, so what should we do to solve for x? We've been doing it. Practice problem number 9. Yep, we'll take power, right? Take the power using the reciprocal of the exponent. So 1/3 times 3 gives you a 1. Whatever you do to one side, got to do to the other. So how about x is equal to 6 times 6 times 6? Are we okay with 216? On this side, do the same thing here. I'm going to take the power using 3, power of power property. In this case, it's 1 times 1 times 1. Hey, that's fun. Still a 1. Cool, no need to check. Those are the answers, and we're done with that. Okay, I'm going to give you one of 2 types. I think there's 4 different types on the homework. Okay, I think between these 2, I think you guys should be able to figure out the other 2 pretty easily. Okay, that was the basic sort of kind. You should see it, but again, the whole concept is, can you take something, figure out what that middle term is, and think about whether the first term is really being a square of that middle term. That's how you want to get it in, and if it is, then you got yourself what you want to be in. Of course, they're not always that simple. So we got this one. But this is cool though. We're sort of like at the height of the algebra stuff. This is the height of algebra. All right, so you guys tell me, what should be the u substitution? Yeah, 1 plus 1 over x. That's easy enough. 1 plus 1 over x. And if that's the case, that first term is not just u squared now. Minus 6 u plus 8. And the question is, can I factor that down? As you guys are finishing up that, of course I gotta tell you a little story. Let's see. Who have I been reading? Oh, I've been reading about Isaac Newton. He grew up, he was a preemie baby. And so he was actually not supposed to live at the first place because he was just so small when he was born. And he was always sick as a child. And that sort of made him sort of the outcast in the school and stuff. So what he did is he took himself to sort of just start doing math. And one of the quotes that he did was interesting. He wrote was it was an interview. He's already a college professor. He just did some major humongous proof in mathematics, and the interviewer says, how do you do it? How do you come up with these brilliant mathematical ideas? And he says, well, all I do is I tackle a problem. I think about it a whole bunch, and I just keep on thinking about it, and I make sure that I just sort of always in the back of my mind sort of thinking about that problem that sort of is, until I finally figure it out. And then what I do is I walk away from it for a while, and then after a while I come back to it, and usually it makes a lot more sense. And so if you guys are stuck with these kind of problems here, it may be a good thing to sort of work hard at try to figure it out, walk away with it just a little bit, and then come back sort of refreshed and sort of look at it again. Maybe might help. I'm saying it will. I'm not saying you're going to conquer the rest of mathematics here or become a brilliant mathematician, but maybe you might. Okay, factored form. You guys ready? U minus 4 minus 2, is that right? How about u equals 4 and u equals 2? The only problem is that's not the end, because now we've got to back substitute everything in. 1 plus 1 over x is equal to 4, or 1 plus 1 over x equals 2. Ooh, that's weird. Got everything inside here, don't we? We have this weird form, quadratic in form, that we had factoring itself, and now we're down to a rational equation to solve. 2 of them. Okay, so let's go for it. Let me rewrite the bottom two. Let me rewrite the bottom 2 equations we had. This one, and this one. Okay. All right, so I guess we should start here. I think we started this today. Let's see. Don't we think about what can x not be? Is that right? And is it the same for both? Is it the same domain restriction for both problems? Yeah, it is, huh? So off to the side, maybe. How about we get, still not. How about, I'll put D for domain. D for domain is that x cannot equal, what do you guys say? Yeah, 0. So again, if we get a 0, can't use it. But let's go for it. Multiply both sides by x, because that is the common denominator. So x times 1, as we multiply the x in, the x cancels, leaving us just with 1, and the other side is x times 4, which is 4x. So let's see, how about subtract x from both sides? Leaves us 3x, divide by 3, and how about an answer of 1/3? Going to the other side, we're going to do the exact same thing. Let's multiply both sides by x, see what cancels, and finishing it off. And you should get x equals 1. Okay, so we spend an hour and 10 minutes on this section. We could spend some more because there's this next problem about time travel. Oh, sorry, I didn't finish up this problem. Sorry about that. Let's go for this first here. X times 1, x times x. Canceling off the 1, there it is. How about a 2x on that side? And how about subtract x from both sides? Gives us 2x, subtract x is x, and x is equal to 1. So there it is. Those are 2 answers. Good there, 1/3 and 1. Okay. All right, something about traveling the speed of light, and I don't know if your physics instructor or teacher in high school ever sort of taught you this. This is kind of interesting here. So let me let you guys read this here first. We're not going to do the, let me just kind of run through the example problem because we don't have the time to do so. Cool. All right, again, omega 1, I think that's a real solar system here, but she took off. She went traveling. She lands back on Earth 15 years later, according to her watch. It finds out that Earth itself is actually 10 years older than she anticipated, which is kind of weird because time is actually relative to the mass that we are on. Technically, it's Earth. The weird thing is, if you were to go almost the speed of light, we could pack up, we'd take our little nap, take ourselves a little lunch, board on a rocket, and if we could go the speed of light, we could go to Jupiter. We could have ourselves a little snack, if we could breathe the atmosphere there, beside the point. And then we could pack up back in the spaceship and go the speed of light back to Earth. We'll find out on Earth has aged 18 years, and we just had a lunch. That's kind of cool because Albert Einstein, he figured out that light actually controls time. And so, in fact, if you live in the mountains, you will age a little bit less than you were to live sort of on solid ground, just because the way light bends. Kind of weird. Another weird fact. Yeah, if our sun exploded, right? Let's say it exploded. Well, the light rays of the sun still have to hit the Earth. We're good? Since light controls time, we actually won't know that the sun exploded till 8 minutes and 20 seconds afterward. Weird other thing. I'm looking at you guys and you guys looking at me. I'm really not seeing you guys at all. I'm seeing like a millisecond later. So when you blink, I actually don't see the blink. I see the blink millionth of a second later, because I'm still having to process that light. Time of light takes from your eyes to my eyes. There is still a fraction of a second that's still built in. Isn't that kind of weird? Talk about fun physics. What else is there? The other fun stuff here. In black holes, right? Because you figure if light controls time, right, the light has to travel. In black holes, there is a ring on the black hole where the light is, and light is actually, what a black hole is, it actually sucks all the light in that place, right? And so the question really in physicists' mind is, if light, there's a, I forgot, it's the circle of something. Anybody help me out here? Black holes. There's a point in which the light that was inside that circle went into the black hole and is no more. Then there's light that escaped the black hole, which is coming out of the black hole. But then there's also this ring where the light is not going anywhere because it's right in that middle. And the question of physicists is there time happening right there? Is actually time standing still? I'll let you guys, whoever's going to be the next physicist can figure that one out, tell me, okay? Okay, so we're going to do this one, but in the book, all we're really doing is looking at a formula. I'm not going to take a look at that here because I want to go through the next section rather quickly. So basically, if this is the formula for time travel, or light travel, which then it becomes time travel. All right, so then again, we're going to skip this part here, but if you're interested, looking at example number 12, practice problem number 12, if you sort of interested in that concept. I'm going to stop here with this section because I still want to go through the next section. Okay, now we're going to deal with equations, but mostly we're going to deal with inequalities as well. So we're going to touch on these here. As I look through this, there's not really anything new that you guys have not seen in algebra already, except maybe the last problem itself. So let's go ahead and sort of quickly let me introduce it. I'm going to skip some practice problems here as well, just so we can make it in time. Okay, so this is 1.5. We're going to try to finish up 1.5 today here. Alright, I guess the only consideration is, remember, if you were to multiply or you divide through by a negative, what you have to do is you have to switch the inequality. I think you guys have learned that in algebra, right? Alright, the other thing that you may not have thought about yet is this part right here. Let me jump to it. Let me just show you this. What do you guys say? True, not true? What do you guys say? Yeah, if you were to take any number and you were to square it, that number would always have to be either 0. If you square 0, it's going to be 0. But if you square anything other than 0, negative or positive, squaring that will make it end up being a non-negative number. Okay, we're good there? That's the only sort of really new piece of information here. So let's go with one practice problem here, something you guys should know. Alright, I'm going to keep time here as well. It's 6:31, so I'm going to try to get through here in a half an hour, which I think we should be able to do. This would be easy enough of a section to do so. Alright, let's you guys try it first. Go ahead, if you can keep ahead of me. If you really are stuck, then you can wait for me to do it and we'll do it together. Alright, what I would do here first, I would distribute probably that 2 times x, 2 times 6, so everything else remains the same. And then I would gather together all the like terms on either side, so only on the right hand side I think I could put the 12 and the 1 together. That should make a 13. I think you guys are a-okay there. Hopefully you have already solved the problem. So how about subtract 2x from both sides? That gives us 2x on one and clears out the x's on the other. Alright, and how about subtract 9 from here? Subtract 9 from here, giving us a 4. Divide by a positive 2. Since it's a positive 2, we're dividing by. No change in the inequality. Cool. Okay, the instructions. I guess I should read the instructions for you guys too here. Solve each inequality and graph its solution set. So graphing this here, and if you, I think you guys should realize this from Math 61, you can find the 2 anywhere you like, but you're saying x is greater than 2. What you're going to have is you're going to have a parenthesis, and the parenthesis has to sort of face the direction you're going to go. So don't do an open dot, don't do a closed dot, you got to use those parentheses. And it's going to go this way, and what you want to do is you want to make the arrow bigger as well, because you're saying with the arrow you're saying it's going to keep on going. If you don't make the arrow bigger, you're technically saying it's stopping there somewhere. Okay, there's the graph, but we also have to write the solution set. What's the solution set here? It's parentheses 2 comma infinity. Okay, good there. So real quick here, overview, open dots, you're going to write in parentheses for open dots. Closed dots, you're going to put in brackets for closed dots. So if you want to write that in, be sure to write that in if you guys have seen it here, off to the side here. So open dot, you're going to put in a parenthesis, just kind of depending which way you're going, like this. If you are used to doing the closed dot, you're going to put in brackets, and again, brackets kind of depending which way you're going. And again, brackets more look like this. Okay, good. Let's try one more here on this type, and we'll jump to some other ones here. Alright, again, I'm going to start it as well here, just so we're going through it here. So first of all, I got to solve for x, so I'm going to subtract 7 from both sides. Negative 2x is greater than or equal to negative 10. divide through by -2, and of course the big alarm goes off in your head. Yep, you divide it through by -2, you have to switch your inequality. Alright, now we're saying x is less than or equal to 5, which means we have a number line with the 5 there, but now we've got ourselves brackets. And then the brackets go towards the left with arrow being a whole bunch bigger. So then can you write the solution set for it? Cool. And let's see what I got. Negative infinity to 5 now with the bracket. So it's going to go off to the left. And with intervals, remember, you always go from less to more, right? You always go from the left-hand side to the higher side. Okay, let's keep on going, and slightly faster if we can. Let you guys tackle this one real quick. And again, it's going to be really one of each type, just really quick here. This is one type. We're going to handle the other type and keep on going. Alright, I'm going to try to catch up to you guys here. So 2 times 4 turns into negative x plus 6x on that side, less than 4 times x, 4 times 1. Putting like terms together on the left makes a 4x plus 8 or 8 plus 4x, whichever way you want to write it. The other side would probably be a 4x plus 11. Alright, and you subtract the 4x from both sides, and then that's the weird stuff begins. So now the only question here, the x's are gone on both sides, and if that happens to be the case, just like equations here, the only question in your mind is this true or false?
True.
Yeah, true. 8 is less than 11. Okay, so that means the answer is all real numbers. No matter what you plug in for x, the left side will always be smaller than the right side. Alright, that's the all real answers. That's more like the solution here. If I were to tell you to graph it or put into a solution set, you would go from negative infinity to positive infinity, which means the whole entire number line is filled in. If you ever want to see a graph of it, you'll just you'll draw in the whole entire number line. Alright, and remember that little weird symbol for all real numbers? Anybody remember that symbol still? Cool, yep, that was sort of a little double bolded R here. Again, do you need to know it? No. Unless you go into theoretical mathematics, you'll see it, but okay, that's one type. The other type, how about you guys get started on this one? Try to catch up again to you guys here. So 3 times x, 3 times minus 2, 5, 7 times x, 7 times negative 1, negative 4 times x, and negative 4 times a negative 2. Careful here at the end. That should become a positive 8 over here at the end. Gather together like terms here, negative 6 and 5 makes a negative 1 here on that side. And let's see on this side, a lot of stuff here. 7x minus 4x makes 3x. Negative 7, positive 8 make positive 1. Alright, subtracting off the 3x to move all the x's over to the left, and again what happens? Same exact thing. Answer is? Cool, you got it. No solution this time because the answer, the inequality is set and it's a false inequality, so can't happen. You can't have a certain thing to be true. And in mechanical engineering, you can't have more output than you have the input. There is always a loss of energy in every single transaction, all the good stuff, all the nice laws of chemistry. Okay, so we got, let's see, we did problem 1, which we saw solve it, graph it. The other side of problem 1, we saw that you have to switch the inequality. Sometimes when you divide through by a negative. The last problem, we saw sometimes you can have all real numbers. This one you can have no answer whatsoever, no solution here. Let's jump to compound inequalities. So remember, compound inequalities, they are two inequalities that is brought together by an or and statement. Okay, I'm going to go a little bit faster here just because of time constraints here. So this time it's an or statement. So we've got to solve this whole entire side here. Then we've got to solve this whole entire side over here. So in this case, adding 5 to both sides gives you a 12. Divided by 3 gives you x is greater than or equal to 4. Solved. That's good. Before we start graphing it, let's go to the other side. And let's do the same. In this case, I think I need to subtract 5 from both sides. Leaving with a negative 2x here, greater than or equal to negative 4. Cool. Divide through by negative 2. Alarm goes off again. Are we good there? X is less than or equal to positive 2. And can you guys graph these on one graph here? What does it look like? Here's my graph here. I guess 2 will be on the left-hand side, and it's a bracket that goes off to the left with a big arrow. Is that right? It goes to the left, right? On the other side, x greater than or equal to 4. That means there's 4 on the right-hand side of things. It's still a bracket, but this time it goes off to the right, and again, filled in with a bigger arrow. All right, then can you write it interval notation? There's a gap in the middle right here, so be careful with that here. Interval notation sort of looks like this, negative infinity, because we're coming from the left. We're going to go all the way to 2 with a bracket. But to show that there's a gap over here, what we do is we put a little thing called union. You're saying it's this answer and this answer here, right? Both sides are answers. Okay, so bracket 4, comma, positive infinity, done. So there's my interval notation. Interval is the way we normally answer the question, because we don't really want to make a graph each time. So interval is the way we show the answer. Okay, so there's an or statement for compound inequalities. There's also an and statement for a compound inequality. That's the two ways to put it together. All yours to try yourself. So the or sort of goes out 2 different directions. The and sort of bubbles up in the middle. That's the one you want. And the and statement really is trying to figure out when both sets are true at the same time. When is the left-hand side true and the right-hand side true? What time interval or when? Alright, distributing the 2, and again, got to work with me here. Keep up if you can. If your mind is still going. Like term, 6 minus 3 is a 3 as well, so how about a plus 3 on that side? Let's see, subtract 3 from both sides gives you a Negative 2x less than 2. Divide through by negative 2. Everybody okay with x greater than negative 1? Cool. On the side, distributing the 2 times x, 2 times negative 5, plus 7 greater than or equal to 3. Cool. Let's see. Gathering together like terms, so negative 10 and 7 makes a negative 3, or minus 3. Adding 3 to both sides gives you a 6 on the other side now, and divide by 2 gives you x less than or equal to 3. Okay, what does a graph of an and statement look like? If we begin with negative 1 here, bracket or parentheses?
Parentheses.
Ah, good. To the left or to the right?
And to the right.
To the right, because it's x greater than negative 1, so parentheses this way. X is less than or equal to 3. That means that's a bracket, but this time going off to the left. So notice that little and statement is the bunching up in the middle. So when are both inequalities true? Any numbers from negative 1 to 3. A while back here, there's a Tom Hanks movie, I think it's a Tom Hanks movie, it's called The Widowmaker. It's about the Russian submarine, the first nuclear submarine, which the Russians invented. And when they went down, there's the engineer. He's looking at, because it's a nuclear sub, so there's a nuclear reactor inside the submarine itself. And there's always this talk about pressure and this talk about temperature. There's two things, and both of them have to be sort of within a certain range. And so it always reminds me whenever there's this and statement that says this has to be within a certain range, and this one, if either one of them are off, then you're in somewhere else, but not in this life. Okay. Okay, there's also the and statement has, and only the and statement has it, is a quick way to do it. There's a short notation for and. So let's cover that real quick here. But before we do that, let's write the interval notation. Everybody okay there with the interval notation? Negative 1 in parentheses and 3 with a bracket. So short notation for and. Or does not have any short notation. That's no fun. But and does have it. Looks like this. Yeah, I don't want that anymore. It can be taken out. All right, so first thing we should notice something. Is that whenever you write short notation for and, you always have a less than symbol or a less than or equal to symbol. You're saying this is the sort of the low number, this is the high number, and this is caught in between them. So it's either going to be a less than symbol or a less than or equal to symbol. Cool. All right, how do we work this? We've got to get that x by itself, so we're going to add 2 here, but we're also going to add 2 to this side as well as 2 to the other. So really you're working on 3 different sides. So negative 6 plus 2 is a negative 4, less than or equal to 4x, and then less than 6 now on that side. What should we do next? Divide by 4 on this side, as well as that side, as well as the other side. Cool. All right, and if that's the case, when you do that, this is the fun thing about short notation for and. You're good to go. There it is. You're saying that x is between negative 1 and 3 halves. So if you were to make a graph of this, looks like this, right? A bracket at negative 1, a parentheses at 3 halves, and everything bunched up in the middle. So all the numbers that are in between negative 1 and 3 halves. Okay, and final answer, negative 1 comma 3 halves. That's pretty easy. It's pretty easy to go from short notation into the solution set, as well as the graph, because all the information is there. All right, so sometimes we actually don't want to go this way. We don't want to solve for x. What we do is we actually want to go the backwards way. We want to form an equation or inequality, a compound inequality that has whatever we want in the middle that we want to have it. Kind of weird to say that. We'll look at one here. So abstractly, here's what we got. Assuming that negative 3 is less than or equal to x and less than or equal to 2. I want to find parameters a and b so that 3x plus 5 is between those two parameters. So we're going from the interval that we like to have into an interval that we want to see in the middle. Alright, so we're going to start off with this right here. So the first question is, what should we do to get a 3x in the middle? So let me do it this way here. We start off like this, right? The red stuff is the problem itself. We start off what we stated is true. I'm going to try to get a 3x plus 5 in the middle here. So first of all, I'm going to do the multiplier first. What should we multiply by? Well, if that's a 3x and that's x, I think it's going to be 3, right? Multiply here by 3, multiply here by 3, multiply here by 3. So we're sort of building up to that end result here. So I got -9 less than or equal to 3x less than or equal to 6. What should I do now? Add 5. I'm going to add 5 in the middle. We're going to add 5 on the left as well as on the right. Everywhere we're going to add 5. So we got ourselves a -4 less than or equal to 3x plus 5 and 11. So there it is. There's our markers. Cool. So then the a and the b are a is equal to -4 and b is equal to 11. So there's our parameters in a sense for the bigger equation here. Okay, so again, a is equal to -4, b is equal to 11. Okay, this is sort of abstract here. Let's look at a concrete term. Don't need to write down the next problem because we don't have time for it. I just want to show you where this stuff is at. Let's say we have a degree Celsius is between 15 and 25 degrees, and something needs to stay in that range so the submarine does not blow up. Kind of important if you're on the submarine. The only problem is our instrument panel is in terms of Fahrenheit, not Celsius. So we want to convert this interval that's in the Celsius measurement, we want to convert it into a Fahrenheit measurement scale. And so if this is the case, everybody agreed here. Sorry, right here is good. Celsius scale has to be here. And then we look at a conversion. This is the conversion from Fahrenheit to Celsius. So if we take 9/5 times C plus 32 gives you the Fahrenheit scale. So what we do is we want to put in a Fahrenheit scale in between here. So let's see what we're going to do first. We're going to multiply both sides by, or everything by 9/5. Then we're going to add 32 everywhere. And now, aren't we in Fahrenheit scale now? So then I can say, oh, okay, now that's what I want. So in order for the Celsius scale to be between 15 and 25, the Fahrenheit scale has to be between 59 and 77. We good? That's kind of a good application of it. I thought that was a good example in the textbook here. All right, but we do have to hit these last two problems left here. 1, 2, which you probably have not seen in algebra. So what happens if you have x squareds while you're doing inequality? What happens there? Figure out where our zeros are and do test points. Something we do for polynomials later on. So first of all, let's do this here. Let's move everything over. And there's no way to tell this right here, as we'll see with polynomials here. So what we do, instead of figuring out where it's less than 0, what we're going to do is we're going to figure out where they hit 0. Because the interesting thing about graphs, if you are in the positive numbers, you want to go into the negative numbers. Do you have to go through 0? I don't know. Let's take a look at this here. If I have a graph that looks like this, and I'm this point over here, and I want to go to this point here, I'm positive, and I can't lift my pen off the paper. Do I have to hit 0 sometime? Yeah, I have to hit 0 at some point in time. I'm going to have to hit right here. We good? Same thing if I turn around. Now when I go back up, I'm going to go here. Do I have to hit the 0? I got to hit the 0. There's no other way without lifting off my pin on the ground. I'm going to hit the x-axis sometime. We good? So that's what we do here. We set it equal to 0. We're going to figure out when do we actually hit the 0. Because when we hit the 0, we know that we might have a change. Do we must always have a change? Not really. It could be going like this, right? It could go hit here and then come back up, right? It doesn't necessarily have to change. But if it does change, it has to go through 0. Factored form. X minus 4x plus 1, is that good enough? And set each of them equal to 0 and solve. How about x equals 4 and x equals negative 1? So what do I know so far? Well, I know that if I have a graph, I'll put these little dots right here. Dot there and dot there. And the dots are that it's going to hit 0. So now I'm going to think about intervals now. My intervals are anything less than negative 1, I know it's going to stay the same sign, right? Because if it would have changed signs, it would have hit 0 sometime. Between negative 1 and positive 4, I know it's going to stay the same sign. And then anything greater than 4. And I know it's never going to change signs from positive to negative, because why? Then it would have had to hit 0 somewhere over here too, right? Okay. So let's go with it here. Let's go with checking this out here. So I'm going to re-graph it just real quick here there. So this one, and this one. We got 3 things to check. So give me a number a little bit less than negative 1. Negative 2. Look at that. I'll go with that. I'm going to check negative 2. I'm going to check it against the original problem. And my question is it true or false? We got 6 is less than 0. That's not true. Bless you, bless you. All right, and now I need a number between negative 1 and 4. The easiest one is 0 is the easiest one. So let's check now 0. So we're doing a test point here. 0. So plug it in 0, blah, 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 blah. And I get this, true or false. Hey, it's true. Cool. Okay, so that little middle section, that's actually true. And I know it's true all the way from negative 1 all the way to 4. Because when I tested 0 is true, I know everything else is true in that interval, right? Cool. And then check 5. Something that's higher than 4. And what do you guys say? True or false for that one? False here. How about 25 plus 2 more on one side and 15 plus 16 on the other, and that gives a 27 is less than 21, and I don't think so. So again, these are nonlinear inequalities. How we do it, we figure out where they are equal to 0 and when we test each one of those intervals. Okay, one last problem and we're out of here. Rational expressions in terms of inequalities, or rational inequalities. All right, first and foremost, we don't want to compare anything to a number besides 1. I'm sorry, besides 0. 0 is the one we want to compare to, right? Because just like with the quadratic equation here. So before we do anything else, let's move this little 1 over. So 2x plus 5 over x minus 1, subtract 1. Now what I want to do is want to make this in terms of just a single fraction. So I got to get some common denominators. What's my common denominator? It's x minus 1, right? Because this guy 1 can be 1 over 1, right? But x minus 1 is going to be our common denominator. And see if this is okay with you guys. Is that good? 1 has now changed into an x minus 1 over x minus 1. All right, a little bit more work here just so we can finish up here. So common denominator is x minus 1. What's my numerator? 2x subtract x would make an x, is that right? And how about 5 subtract a negative 1?
6.
Plus 6 is good by me, okay. Less than or equal to 0. Okay, so what we've done is we've transferred everything over so that we are now comparing it just to 0. That's very important because we're looking at the real number line now. Okay, so let me just rewrite it real quick here, since you guys already have it on a sheet of paper. And then what we do, this is sort of off a little bit here. Let's see. I'm going to take just the top itself. Forget about the denominator just for a little bit here. Just the top itself. I'm going to set the top equal to 0. So x plus 6 equals 0. And here's what I got. Let's see, what's my problem with my domain? 1 is a problem, huh? There's never a time this guy could equal 1. So what we do is we put a little open dot right at 1, not a closed dot. And then negative 6 is going to be the other one. At this point, we are going to put a closed dot because we're saying a negative 6 is actually goes through 0. And a positive 1, we have ourselves a break in our graph. That's the little open dot means. There's a break in the graph. So, like we did before, let's choose some intervals here. So something less than negative 6. I'll go with negative 7. Plugging it in. A number between negative 6 and 1. I'll go with 0. And a number bigger than 1. I could choose 2, I could choose 5, I could choose 10, it doesn't matter. As long as it's bigger than 1, and I know it's never going to change signs again because it should have hit 0 by then. Okay, and almost done here, just real quick here, and we're done solving this guy. I'll leave this up here for later. So negative 1 over negative 8 will become a positive 1 over positive 8, and that's going to be a no. Checking 0, 0 becomes a true statement. And what I'm doing is I'm using this inequality right here. I'm just comparing it to 0. You could use the original inequality as well, but it'll still give you the same answers. It's just a lot easier to compare it to 0 instead. It works for 0, and then it does not work for 5, so nothing there. So I got myself that little green area. How do we write the final answer in interval notation? Notice we are going to include the negative 6, but we don't include that 1. So I have a negative 6 in brackets, 1 in parentheses. Okay, good there. So hybrid day on Thursday. Ryan's going to be there at 6 to 7:15. If you guys want some homework questions here, you guys go to the YouTube video, which will probably be posted by noon. Probably on noon on Thursday. I'll probably post the hybrid video. What's up, George?
How are tests?